Hello everyone, my name is Aline Bornet. I am a PhD student at the University of Bern in the group of Matthias Ahrens. I am part of a large collaborative European project called RECYCALYSE. And today I would like to introduce you to the result obtained by testing iridium oxide and iridium ruthenium oxide nanoparticle for the OER in a gas diffusion setup. What is the motivation behind this project? To make the electrochemical water splitting more efficient, new catalysts need to be designed for the anodic reaction, especially if we want to use this technique as a storage for excess of energy supplied by renewable sources and therefore reduce our dependence to fossil fuels. In this respect, I developed 4 catalysts that I tested in the GDE setup that you can see here. And here you can find a cross-section of the setup. Here at the anode, the reaction of interest, the OER, takes place. In this publication, where I am also a co-author, you can find more details about the screening device. Let's go into the actual experiments. Using a surfactant-free colloidal approach, I could synthesize iridium and iridium ruthenium nanoparticles that were deposited in a second step on either carbon support or commercial ATO support. As characterization, TEM images were taken to determine the mean particle size of the 4 catalysts. All of them has a size of about 1.5 nanometer. I then proceed to prepare the electrode by depositing the catalyst on a coated gas diffusion layer, GDL, via a vacuum filtration setup. By EDX mapping, we can see how well the catalyst is laying on top of the GDL and how homogeneous it is. The performance of the catalyst is then screened first in terms of activity by stepping at different current every 5 minutes. The influence of the temperature on the activity is first tested by using 3 different temperatures, 30, 40 and 60 degrees. With this data, I can compare the influence of the composition and the support on the activity. The comparison is made at 60 degrees as high temperatures are usually used under realistic conditions. So if we compare iridium and iridium ruthenium, we can see that by adding ruthenium, the activity of the catalyst is improved as expected. The supports are then compared using iridium as catalyst. At low current density, iridium on carbon is more active, but the trend is inverted when increasing the current density and iridium on ATO becomes more active. We attribute this effect to the oxidation of the carbon support and maybe to an increase in the ATO conductivity. Our GDE setup can also be used to perform stability experiments. For that, I perform a single potentiostatic step at 1.6 volt for 2 hours at 60 degrees for each catalyst. First, we test if the stability is loading dependent, and we can see on this plot where the normalized current density are against the time that there is no significant difference between the 2 curves, and we can then say the stability is loading independent. Then the different supports and material are compared in terms of stability. On this plot, 3 conclusions can be made. First, carbon support is less stable, it has a higher slope. Second, ATO support itself is not causing further degradation. And finally, by adding ruthenium to iridium catalyst, the stability can be sustained. With that, I come already to the end of my presentation. I just need to add that some further experiments will be performed to better understand the implication of the GDL on the degradation. I would like to thank you all for watching my video. If you want to have a deeper insight into my work, I prepare a video for high school students that you are welcome to watch here. It is in German. And if you are interested in learning more about RECYCALYSE project, you can visit its official webpage. Thanks again, and I hope to see you during the discussion. Bye!